I think. All right, everybody. So we'll start here. So thanks for showing up to this webinar. Thanks for taking the time to listen. It's been a while. I think there was a first series of a webinar 2 years ago, but now there's a new call for proposal out, and I think it's time to discuss James Webb proposals. So contrarily to what the first slide shows, we're not going to talk about the man who gave a name to the observatory, but we're going to talk about the observatory itself. And you know, this is, I should first point out that this very presentation is on the web. If you go to jwst.astro.umontreal.ca and click on the webinars tab, you'll be able to download this presentation PDF format. There aren't that many slides. Really, today it's about a live demo mostly of the tools. But if you prefer the PDF version, feel free to go to that link. First thing I'd like to mention is that you may ask questions during the webinar, but there's going to be like a couple of questions, space of time at about the midpoint, and at the end we have 30 more minutes for more questions if you want to stay longer and have questions. So so that's it. And so I'll try to give you, a brief overview of the observatory capabilities. And now that Spitzer has been retired as of today, and there's only HST still orbiting, we have James Webb that will fulfill most of the science done by those two observatories and more. So I will talk about the science that can be done with this great observatory. Then I'll go over the call for proposal itself and give you some more interesting details. And then we'll talk about a little bit about instruments, not much, but more about the documentation page and the website that the Space Telescope has that you should be really looking at. And there's going to be a live demo of the astronomer proposal tool, the APT, and the exposure time calculator given by my two companions here in the office. And we're going to have a last word and give you what's coming. So first thing, I should mention that I'm Loïc Albert. I work here at the University of Montreal. And my teammate here today are Neil Cook, who's going to give the APT demo, and Geert-Jan Tallens, the ETC demo. If you have any question regarding James Webb, you can always send us questions with the JWST help@astro.umontreal.ca email, Elias. We're a small community and we're a small team to help, so feel free. It's supposed to be, we're supposed to be here to help you if you have questions. Of course, there's always the bigger help desk at Space Telescope, but don't hesitate to contact us. So why in Montreal are we talking to you about James Webb? It's because Canada has built one of the 4 science instruments on board James Webb. We've built the fine guiding sensor and the FGS and NIRISS. And it's there in the instrument rack along MIRI, NIRCam, and NIRSpec built by our partners in this project. The PI of the instrument is René Doyon in Montreal, and so we're very proud to see it. So the NIRISS is built by CSA through the contractor Honeywell in Ottawa. All right, so what about the latest news of the observatory? There's good news, in fact. The telescope that you see here, so the mirrors and the instruments in the back, they've finally been united with the rest of the observatory, with the spacecraft. That is mostly the sun shield here, the 5 layers of Catton that are supposed to shield the telescope from the sun and get the telescope very cold. It's an infrared observatory, so it needs to be cold. So they have been united together, and that was in the fall, I believe last year. And now they're undergoing, what they're doing is folding those layers of sun shield back in preparation for a vibration test, the final vibration test of the observatory. After that, they will deploy the whole observatory again, and they will test it to see that everything sustained the vibrations, and they will fold again to be able to ship it to French Guiana for launch. So the shipment should happen at the end of this year. So there's a lot of activities still this year with testing, and testing is occurring in California at the Northrop Grumman installation. Okay, so James Webb really is going to be a game changer, I believe, for observations in the near infrared, especially in the mid infrared. So James Webb is going to explore a totally new window of wavelength between 2.5 microns and 5 microns, where we have little capabilities from the ground because of the atmosphere, and the Spitzer didn't have a sensitive instrument in that domain much. So James Webb has a big gathering power. It's in the 5 to 10 micron domain. James Webb is probably more sensitive than Spitzer by about several hundreds. So any observation in that wavelength domain with James Webb is going to be a new discovery. So that to me is a very exciting part of James Webb. So it has 4 instruments, and here you can see a footprint of their field of view in the focal plane. So 4 instruments means lots of different observing modes. And I will not, unfortunately, don't have time to go through all those modes. I'm going to spare you that. But suffice to say that NIRCam in the center has two modules to do imaging. On the left, you have NIRSpec, who is a spectroscopic machine in the near infrared. It can do long slit, multi-object. It can do IFU, so integral field unit spectroscopy. On the right, you have MIRI, the mid-infrared instrument, working between 5 and 28 microns. It has all of the capabilities: imaging, spectroscopy, coronagraphy, integral field units, so lots of modes. And on the bottom right, you have NIRIS, our Canadian instrument, which does wide field slitless spectroscopy and essentially exoplanet atmospheric spectroscopy. The field of view are of the order of about 2 arc minutes here. So it's small field of views, but and the arrays are 2K by 2K arrays for the near infrared. Here's another way of putting together all of the modes that you can observe with. And I've already said there are 17 observing modes, and they cover essentially imaging and spectroscopy. Spectroscopy goes up to a resolving power of about 3,000 and as low as 100. And so you have a lot to choose from. And of course, with this diversity comes a lot of science themes that can be tackled with James Webb. Assembly of galaxies, first light and reionization, the birth of stars and protoplanetary systems, planets and origins of life. So there's a wide variety of things you can do. And I don't want to scare you away from applying, even though you may know that there's already allocated time on James Webb. That is the guaranteed time observations, the GTO. This consists in essentially the instrument team people. There's about 4,000 hours already allocated, and they're going to be used in mostly cycles 1 to 3. And they cover more than 100 science programs, okay? But JWST observes 24/7, so you have a large number of hours in a year. It's not orbiting the Earth. And so that leaves a lot of time for the general observer. About 6,000 hours are expected to be given in the first cycle. There's also an early release science suites of 13 science programs, and they will, those programs are going to be observed very early after commissioning. and they use up about 450 hours. And their data is going to become public as soon as they observed. You can have a full and comprehensive list at this link here. So I want to give you ideas of what James Webb can do. Here you have 3 images. On the left, you have the actual Hubble XDF taken with WFC3, the near infrared for 65-hour integration time. And on the middle is an expected snapshot in only 2 hours with a 3.5 micron filter, medium band with NIRCam. And you see you're going very deep in only 2 hours with a medium band filter. On the right, it's actually spectroscopy with NIRCam, with a GRISM. And there you can tell all of the emission lines that those galaxies harbor and produce. And you can, define, you can find out the redshift and all of the chemistry or whatnot. So it's a very powerful game changer for deep fields. For the exoplanet community, which I belong to, it's also a long-awaited machine. It will observe atmosphere spectra of exoplanets, a lot of them, in relatively short integration. So here we have the spectrum of an atmosphere for a planet WASP-79b. And we have essentially a simulation using 4 different instruments that cover from 0.8 to 5 micron. And what's new here is that we open into a new wavelength domain that for now only HST with WFC3 can only achieve spectra between 1 and 1.7 micron. Now we're covering up to 5 microns, and that helps us get a much more precise measurement of the metallicity and the carbon to oxygen ratio in those planets, and try to constrain their formation. So it's very, there's going to be a ton of great observations in this field. If we go closer to Earth, here's an example of Europa observations with the IFU of NIRSpec, and it's going to be able to take spectra between 2.5 and 5 microns of the plumes coming out of the pole of Europa. So that's very exciting. We're going to be able to tell what are the molecular species in those plumes. So that's very interesting. All right, so I hope I gave you a good taste of what we can achieve with James Webb. Now I'm going to shift gear and talk about the call for proposals itself, give you the timeline here. So we stand here at the end of January. The call for proposal has just been released. The deadline is May 1st. And the launch is currently still scheduled for March 2021. And after launch, there's going to be 6 months of commissioning where we align off all of the primary mirror and the secondary mirror, do the focus of our instruments. And after which, the cycle 1 observations and GTO and ERS will start. So that should be in September or October 2021. Now, the burning question I can almost hear, even if you're all muted, what happens if there's a launch delay, another launch delay? There were news this week circulating that there may be a further delay. If there's a further delay, it's likely to be a few months, not years. So what the Space Telescope Science Institute has repeatedly told us is that the deadline for submission of the proposal is going to stick. They're not going to change the deadline like they did last time at the last delay. So the May 1st deadline is there. You have to bid to it, and it won't move unless there was a terrible problem with testing. All right, so let's go a bit deeper in a few things that you should notice in the call for proposals. About 35% of the time is going to be used by GTO ERS, but that leaves us, the general observers, with 65%. A typical observing proposal is going to be 4 + 4 pages long. It's going to be submitted through the astronomer proposal tool, the APT that we're going to have a demo later. And an important thing is that it's going to be a streamlined proposal. That is, it's not going to be split into 2 phases, 1 and 2. No, it's going to be both phases at the same time. That means a lot more work. You have to define all of the details of your observation, all of the filters, the exposure time, everything at submission. And so a lot more work, and that's why we recommend to start your proposal at least 6 weeks before the deadline. So mid-March. If you're mid-March and you haven't started, it's starting to be late. So I'm glad you're here. It's because you're interested. You might have already started, in fact. Another important news is that the Canadian Space Agency is going to fund successful proposals led by Canadians. So that's a first. That's a very good news. And they're going to, so the details of that funding are not out yet, but they're saying it's going to be at about the same level as what NASA funds the US PI for accepted proposals. The last thing I wanted to tell is about the double-blind review of proposals. So if you're familiar with HST, in the last 2 years, HST has used that review process. So essentially, you know, with the TAC, we don't know who the TAC is, but they in the past they knew who the authors of the proposals were. This time they're going to hide this information from the reviewers. So the reviewers won't have access to the name of the PI or the authors of the proposal. And that's supposed, and it has actually helped in evening out biases, like biases against women, for example, but not only against women, against small institutions, small universities versus good reputation universities. So that really is working for HST, and they will use that system for James Webb. That also means that if you're writing and you have your own work to cite, to refer to, you should not use you know, 2010 we found this and that. You have to give no clue as to who the authors of the proposals are. Yeah. All right. So big red screen. If you keep anything from this presentation, begin no later than mid-March your proposal. All right. Okay, so I'm going to shift gears again a little bit and go into a demo of the documentation webpage for JWST. So before I do that, if there's any small question from what I've talked before, you're welcome to ask it here. And if not, I'm going to continue. So if you have a longish question, we can wait till the end. All right. Everything is clear. So I'm going to talk to you today about the user documentation, everything, essentially the Bible of knowledge for James Webb. So let's go to this web page here. Okay, JDocs. So I'm going to reduce the size. There you go. Okay, so that's the JDocs page with an X, and that's where the truth is. So if everything fails, read the documentation, but you should read the documentation first. And so it's a collection of hundreds of articles about James Webb, and it's set up in a similar way as Wikipedia. You basically have links in the page to other pages, and you go and you hop from one page to the other. And there's a bit of randomness sometimes, but essentially everything is there. Everything is supposed to be self-contained in all those articles. If you don't like that system, you can browse from the left bar, on the left menu. You have a list of topics, and they are essentially in the logical order through which you should go to get information towards submitting a proposal. So you can go that way, you know, proposing opportunities, the proposal preparation, the tools, the instruments, and the data that comes out. So you can go from the top to the bottom this way. Or if you're about to board on a plane and don't have access to internet, you can go directly in quick links and PDF handouts. And those are essentially PDF versions of a version of the whole pages put next together in a single PDF document. So here's an example for the call for proposal, and you know, it's essentially the same pages as JDocs, but in a PDF document, right? So yeah, so you should download all those if you're about to board a plane. All right, so I'll go through a few things that you should perhaps know. Of course, getting started guide is useful. Okay, it gives you different aspects of the observatory, of the detector, the sensitivity tools of the observatory. It gives you a view of all different tools and the calculators that you can have access to, and so on. It's essentially, this webinar here can be, it can be summarized into those steps from 1 to 8, and you can go through them and learn as much as today. So that's one thing. You can go, if you have a lot of time and are a person who likes visuals, you can go to the video collections. You have tutorials for the different tools, for the JDocs, for the APT, for the ETC, and even for, say, the NearSpec MUS tools to select sources when you do multi-object spectroscopy. So there's a good collection of videos there that you can watch. If you have absolutely no idea of the instrument's capabilities, you should look at the pocket guide. It's essentially one page, one instrument guide. Tells you about, in a few figures and tables, tells you about all of the capabilities of each instrument in a quick way. Something that can be very handy, I'm still referring to that, is the list of acronyms. It's unbelievable how many acronyms there are in this project. I've been 10 years on it, and I still am missing out sometimes with acronyms. So there's a long list of the acronyms here for James Webb, can be useful. And also, I mentioned earlier the help desk. The help desk is where, after you've tried to learn the information from JDocs, that's where you go if you still have questions. That's the official, entrance to when you submit questions, is the help desk, and they keep record and they spread the information for other people as well. So you might send us in Montreal an email because we're closer, but if you have very detailed questions, you can ask the help desk. All right, so there's a few more things I wanted to point out in the JDocs. In the proposal preparation, there are roadmaps. Here, methods and roadmaps. That's useful. It tells you, so if you have a science idea, but you don't know, okay, what instrument am I supposed to use? There are so many modes there. So what am I supposed to use for my science? Well, you start here and you say, okay, maybe you probably know if it's imaging or spectroscopy. So you pick, say, imaging here. Okay, so what instruments, so they are put side by side. Each instrument mode is put side by side, and you can quickly compare between the modes of, the similar mode of different instruments. Okay, and it tells you, gives you a better idea how to choose which instrument you want. Gives you the sensitivities and so on. So that's the roadmaps. And there's also, to help you, there are example science programs. So if you've chosen more specific mode, you can go there and get examples to build your proposal from step 1 to the submission of your proposal. So for example, here, if we have a MIRI proposal, there's a MIRI MRS spectroscopy, say of an M-star, and it has a list of all the steps through which you should go in order to get from, which mode I want to use down to, how you fill your APT for that observation. So if you follow all those steps and they give you details for each of those steps, you can build your own observation. So choose the template that's closest to your science program. All right, I'm almost done with this. There's two pieces of information that I think I should cover to help you in what's coming with the ATC and APT. And one is the how our detector read out. So if I go in the detector readout, proposal preparation, detector understanding exposures here, and I go in, get this figure. Okay. So that confuses a lot of people that when they're new to infrared detectors and James Webb. So here you have essentially three keywords that you need to keep in mind: groups, integration, and exposure. Okay, and so if you're used to CCD technology, you know that when you read out a CCD, you actually displays the charges, and you can only read it once, and that's it. It's lost after that. For infrared arrays, you have non-destructive readouts. So that means you can repeatedly read out the detector and build up your integration and signal to noise. And so these readouts are here, the rectangles are the reads, each individual reads of your detector. And for reasons of disk space on board the spacecraft, sometimes it's useful to save on disk space by averaging a few of those reads together. And when you do that, you call this a group. So instead of having a frame or a read, you have a group of reads, and you lose some information, but very little, and that saves, that allows you to download more data. So if you take all those groups together, all those reads, it makes your integration here, your first integration. After an integration, you reset your detector and go to the next integration. So the James Webb, they've decided to put all integrations back to back in a single FITS file. And that's what we call an exposure. Okay, so in an exposure, there can be one or more integrations, several integrations, and in each integration, several groups, or think of the groups as single reads in a sense. If you take images and ditter around, that means that you're gonna create new FITS files for every ditter position. All right, the next thing, the last thing I needed to mention is the field of regard of the observatory. All targets can be observed with James Webb, but not all can be observed all the time. Most can only be observed during 2 viewing windows throughout the year. So James Webb is orbiting around the sun, and I'm looking for my link, the field of regards. There, thank you. Field of regards here, there, I'm getting there. So James Webb is facing the sun. The sun shield gets the observatory cold on one side, and it can rotate. So the observatory can only rotate about this axis between it and the sun. And so it can access a swap of coordinates on the celestial sphere here that's in like purplish color. and at any given date. And this visibility window swaps the entire celestial sphere twice in a year. And so you usually have two observing windows for any given target in the sky. All right, and I'm here. I think that covers the JWST. So I'm gonna let Neil Cook here continue with a live demo of the astronomer proposal tool.
Okay, thank you, Loic, for that excellent introduction. So I'm just going to share my screen. Okay, so basically now you've had a sort of overview of the instrument, we want to quickly go through and give you a really simple example. So the first thing you're going to need before filling out the APT and the ETC is you're going to need some science. Once you've got this, the first thing you need to do is make sure you can observe it. So as Loic said, most targets will have 2 regions, but if for some reason you have some special requirements about when things need to be observed, you really need to check whether they can be observed. So this is done with these tools, and again, all the information about these tools are on JWST. Even there's a background tool, so if you're doing some extragalactic stuff, you might need to worry more about your backgrounds. So for our simple example, we're going to use G13921. It's an A star, and we're basically going to say we're doing some flux calibration. So we want a spectrum between 1 and 5 micron, and we want to have at least a signal to noise of 100 at 5 micron. Now, just for the purposes of this example, we're going to say that the magnitude is 15 in Johnson J in the Vega system. And because it's a calibration, we want it to be observed in September 2021. Oops. Yeah, so on the right here, I'm just basically showing you the setup that we chose to use for this. The actual details of this don't matter too much, but we're going to be using near spec with a fixed slit and no target acquisition. So these will become clear when we get into APT. But just to know that these don't really matter for you for now. But we've chosen these for our calibration. So once you have your science, and you've looked through JWST, you'll be able to decide which mode, which instrument, and all the other various details that you'll need. Okay, so now I'm going to load up APT. So this is APT. First thing to note is that it's version 2020.1.1. This version was released with the call for proposals, and it should be the version you put you do your proposal in. But you'll have to note that on March 5th there will be one last update, and that's the version that you'll need to submit in, and that'll be 2020.2. And again, I repeat, that's March 5th when that will come out. So you have to make sure when you do these proposals that you open in that, you make sure that all of your details are still correct. There is a list of changes on JWST if you're really concerned that it will affect your proposal, but most of them are quite minor. So this APT will be very familiar if you've ever done Hubble proposals. It's the same tool, and you just have to make sure that instead of automatically going to Hubble, you go to James Webb. So as with Hubble, the first thing you do is go to this new document here, and instead of HST, JWST proposal. And that loads up this nice interface here. The first thing you'll note is a load of red crosses. So red crosses are basically errors. You cannot submit your proposal while you have red crosses. Now for this demonstration, I'm not going to worry about this first section. This first section is proposal information, so you guys will be able to fill that out without any problems, but for this example, we don't need to. So we're going to go straight into our targets. So that's the first thing you need to do. You need to define your target. So for this target, we use fixed target resolver. And this is basically a search of your favorite database, Simbad, NED, the two masses there. And we're searching here by name, but you can do positions near and other things like this. So we're going to do this A star, so it's G139-21. And hopefully if you found your target, it will appear in this list and you can click it. and we can select that target as an object. You'll notice that it's given us a warning that it's found proper motion. This is a fast moving star, so that's fine. If you weren't able to find your target, there are lots of other options. So you can actually go do a new fixed target and put in your ARIA deck yourself if you're really sure. We suggest that you do this all with Gaia coordinates because you need to have your accuracy of your positions really good. So use the 2015.5 and the Gaia coordinates if you can. So you'll notice now that we have a nice red cross here. So this is our target here. The one on the front is just a unique number. If you have lots of targets, you'll have lots of these. But if we click on here, you'll see that these errors are really specific. So for this case, we haven't selected a category. It doesn't really matter for this demo, but I'm going to do a calibration and select A stars. And now you'll see that that red X has disappeared and we just get some warnings. And if we mouse over it, you see that the warning is because the target is not used in the proposal. So most of these errors and warnings have really nice, specific and clear messages to tell you exactly what's gone wrong or what they suggest for you to do. So in this case, we need an observation. And if any of these don't make so much sense, you can go onto JDocs and you should be able to find out what your errors and what your warnings are. So yeah, so we have our target. Next thing we need to do is go to observations. So you click on observations, you click new observation folder. It loads up this interface. We're going to go to the first observation. Now you can label your observations, and we definitely recommend this if you're going to do a really complicated proposal. For this one, we're just going to keep it as observation 1. You select your instrument. So first, this is near spec, and we did fixed slit spectroscopy, and you select your target. You'll note that now this warning has disappeared on our target because we're now using this target. That's good. So you guys, if you're using this mode, will definitely need target acquisition, but just to make this a little bit more simple, we're not going to do that. So we can click none here. And so basically all we have now is to fill out the science parameters. So these are the ones that were on the right-hand side slide. So again, the details of this don't really matter. We're going to use the standard slit and subarray. We're going to use no dither patterns, just to make it nice and easy. And on our gratings and filter, you click add. We add our clear prism, and we change our readout pattern to NRS rapid. So you'll note now that it's still not going to work because we have crosses, and this is because we haven't worked out the groups or the integrations. So for this, I'm going to pass over to Gert-Jan. And then once we've done the ETC, we can come back into APT and just finish off so you're ready to submit. Okay, so I'll stop sharing my screen now.
I'm muted in both.
Okay.
Okay. Can everyone hear me now? Can you hear me?
Audio is good.
Okay. So I'll just go back to the beginning. So you go to this website, James Webb in exposure time calculator at stsci.edu. You can work here anonymously, but we recommend that you create a user account for yourself, because then you can keep track of multiple exposure time calculator workbooks and share them with other people you're working on the proposals with. So I'm just going to log in here. And then you'll see I currently have no workbook, so I'll start by creating a new workbook. And then I have this workbook here, and I can load the workbook. So the first thing we'll start with for this observation is setting up our scene. So basically the field and the sources in the field that we're going to observe. You'll see here that there's, by default, there is a scene with a source in it. So we'll select those two together. And then on the right here, this source editor becomes available to set the details of that. So you can set for the scene and for the source, you can set a name, a description, which we recommend you do if you're making a more complex scene than what we're going to do for this. But for now, we're just going to skip this. So then we go to the Continuum tab to select the spectrum that we're going to use. In this case, we're going to use a Phoenix stellar model of a main sequence A0 star. So we've done that, we can save. And then we have to renormalize this spectrum to the correct magnitude. So we said we're going to use a Johnson J magnitude of 15. So we're going to say we're going to normalize this in a specific bandpass. And we're going to use the Johnson J magnitude. And then the normalization we want is 15 Vega magnitudes. And you can see here there's a lot of options for how you want to normalize this depending on Johnson J magnitude, yes. Depending on what your information is or what normalization you need for this. So we can also save that again. And now on the bottom here, you can see this normalized spectrum of the A star. So for now, that's all we need to do for our source and scene. There's other options here. You can add specific lines if you have a specific interest in a particular line. You can do extended sources, or if you have multiple sources, you can offset them from relative to each other. But now that we set up the scene, we can go back to calculations and we can select the instrument we're going to do this observation with. So near spec, fixed slit spectroscopy. And you'll see here, it immediately starts first computation with the default settings for this instrument mode. So we have to wait a moment for that. Yeah, so you can see here, we've run this calculation. We got a signal to noise of 100, but we also have this warning here. So if we select this computation now and go to the bottom here, we can see that the warning is because in this tab of saturation, there are several pixels here that have saturated. And you can see in the groups before saturation tab that these pixels have saturated basically in a single group. And groups are basically the smallest unit you can have. So this is an issue. So we need to deal with that. And actually the reason it's doing this right now is because we haven't actually changed to the instrument parameters we are going to use for this observation. So if you go in here, you have the instrument setup, so it's prism clear and the slit, as Neil just described. But if you go into the detector setup, the readout pattern is still set to NRS instead of NRS rapid, which is very important for this bright source to use the rapid readout pattern. Another thing we haven't changed is that we were aiming to have the signal to noise of 100 at 5 microns. So if you go to the strategy tab, which basically describes how the ETC extracts the flux from its images. So basically the aperture photometry or the sampling, we have to set the wavelength of interest here to 5 microns. So now that we've done that, we can recalculate. And you'll see that we get much lower signal to noise here now, and no errors anymore. So the next step is in the detector setup, determine the groups and integrations we need to get this back to 100 signal to noise ratio. So for the groups, we normally recommend that you try to use the maximum number of groups you can. So we're going back to the groups before saturation plot below, and we're going to check what the groups before saturation are for this observation. You can see here the Z coordinate, it's 15, 14, and we know there's one here somewhere that saturates at 13. So we're going to use 13 groups per integration for this exposure. So again, we can recalculate to see what signal to noise we now get. And you'll see in a moment that we now get a signal to noise of around 16. Yeah, 16.8. So we need we want signal to noise of 100, so we need about factor 6 more signal to noise. It corresponds to factor 40 more exposure time. So we're going to increase the integrations per exposure to 40. And like Neil said, we're not using dithering, but if you were to use dithering for these for your observations, you need to set the total number of ditters here first before you start adjusting these numbers. So we've now set it to 40. We can calculate it again. And we'll find now that we have the signal to noise of 100 at 5 micron that we want for this observation. Yeah, 102.5. And if you go down here, you can also see, for example, this plot which gives you the signal to noise ratio as a function of the wavelength. You can see here the signal to noise of 100 at 5 micron and considerably better signal to noise over the rest of the wavelength range of the detector. Okay, I will now hand back to Neil.
Right, hopefully you can hear me. So now, thanks for that, Kerchan. So now we know what our groups integration should be. So we said it was 13 groups and 40 integrations. You'll also note that there's also a place to put your ETC workbook. This is not required for submission, but it really does help you track which calculation you use to do this, because one of the good things about ETC is you will need to play around, right? We knew what values we needed for these because we played around in the ETC. So we could have had 5 or 10 calculations there. So you can always enter your workbook here, say 10,000, and you can add a 0.1 for your calculation. And that will actually reference back. If you click here, it will go back into your workbook on the ETC. So it's a really good way to keep track of this. And this is the same for the target acquisition as well. So it's a really nice way to do that. So now we have that. Now you'll see that we've got rid of our cross from our observation, but now we have a warning. So if we click down here, you'll see that the warning is due to this visit duration. And if we mouse over it, it's because it says our overheads are provisional until the visit planner has been run. So that means there's at least one more step we need to do. But if you remember back to my slide, there was one other thing we needed for observation. We wanted our observation to specifically be in September 2021. So the place where you add this is in special requirements. You click add, and there's all sorts of options here for all the different things you can require. And for this one, we're going to go between dates, and we're going to go 01 Sept 2021 and 30 Sept 2021. Oops, like that. And once you've entered them correctly, you should be allowed to add it completely. And now that's added that special requirement that our observation has to be between those dates. So the very last thing to do is to go to this visit planner. So up at this top, you'll see visit planner. And we click on this and you'll see all these are yellow because they have not been calculated yet. If we go to update display, it'll take a couple of seconds. And what you should then see is this. So first good sign is that it's a green tick. That means it is actually observable. And if we click down here, it will show you all of the requirements that were used and tested against and tell you what sort of observability each one of those has. So you'll see here that this object, we actually chose it to be nice and observable, but you'll see the breakdown of this, and the most stringent requirement we have is actually our little window here, which is between September 1st and September 30th. So this is all good. Our observation is observable. And one other thing to note is there's these nice reports here. They're not so useful for this one, but they're very easy to lose. And you can actually start seeing which visibilities were good, which visibilities are bad. So if you had those crosses, this is a really good place to remember to go and check to see when you can see your object and when you can't see your object. Okay, so now you've done that. All you need to do is write your proposal, your 4+4 pages, and then you go to submit. You add your PDF with all your information here, and you click submit, and you're done. So that wasn't too difficult for this example. So I'll just hand back over to Loïc now.
Unmute. There. All right, so it's essentially, we're essentially, whoops, we're essentially done here, I believe. We have, this is our last slide. We have a few events coming up to help Canadian astronomers with their James Webb proposal. So this webinar is going to be posted on YouTube with this nearest instrument team user, if you're interested to rewatch it. There's currently a workshop happening at the University of British Columbia over 2 days where they teach you how many details about preparing a proposal. And there's 2 upcoming workshops, 1-day events, March 12 and March 18, one at Western Ontario, prepared and organized by people over there, and one at the Université de Montréal here in English. And also there's 2 webinars near the end of, before deadline. Okay, so it's relatively free at this point. What exactly we're going to do in those webinars, it's intended to answer questions mostly. If you have questions, we're there to answer those questions. So if you have special requests, by the way, you want to have things covered, you feel free to contact us so that we can touch those points and prepare. But essentially, there's going to be a T-2 weeks and T-1 week webinar to get Q&A sessions. And the final slide is the following. It's the take-home messages. So it's red. So if everybody was sleeping now, feel you need to be awake. Begin your proposal no later than mid-March. The documentation JDocs is your friend. It's the documentation Bible. The astronomer proposal tool has the final say. If you see error warnings, anything, the APT has the final say. You have to, it has to agree for the proposal to be submitted. If you have questions, you can contact the help desk, the official James Webb help desk, or maybe contact us in Montreal if you want more personalized help. And you can, of course, attend in person one of our workshops. And you need to begin your proposal no later than mid-March because there's a lot involved in the proposal. So that concludes our presentation. You can contact us and you, at this point, can ask any question. We have a good half an hour more live if you want to stick around. Sound unmuted.